The limiting reactant is the reactant that is completely consumed when the reaction is complete. It therefore limits the amount of product that can be produced by a chemical reaction. The analogy we have to a limiting reactant is making hamburgers. Let's say we have 3 patties, 4 buns, 6 slices of cheese, and 7 slices of tomatoes. If we use 1 patty, 1 set of buns, 1 slice of cheese, and 2 slices of tomatoes to make a hamburger, then you can see that we can only make 3 complete hamburgers from our ingredients on the left. What will be left over is 1 bun, 1 slice of tomato, and 3 slices of cheese. The hamburger patties, therefore, are the limiting reactant in this case, and the buns, cheese, and slices of tomatoes are the excess reactants. Now let's look at the reaction between nitric oxide and oxygen to produce nitrogen dioxide. And let's say we start with 8 molecules of NO and 7 molecules of oxygen, as shown in the diagram on the right. We can analyze the reaction by looking at the initial number of molecules that we start with, the change in the number of molecules during the reaction, and the final number of molecules at the completion of the reaction. And initially we start with 8 molecules of NO and 7 molecules of O2, as was mentioned previously. And since this is at the beginning of the reaction, we don't have any nitrogen dioxide to start with. Since nitric oxide reacts with oxygen in a 2-to-1 ratio, we can see that nitric oxide is actually the limiting reactant, and therefore all of the nitric oxide will be consumed. And it will react with oxygen in a 2-to-1 ratio, so those 8 molecules of nitric oxide will react with 4 molecules of oxygen. And they will in turn produce 8 molecules of nitrogen dioxide. And this is because NO produces NO2 in a 1-to-1 ratio, as we can see from the balanced chemical reaction. Finally, to determine the number of molecules present at the completion of the reaction, all we have to do is add the columns. So we can clearly see that at the end of the reaction, there are 0 molecules of NO remaining, there are 3 molecules of oxygen remaining, and 8 molecules of NO2 have been produced. So here we can clearly see that nitric oxide is the limiting reactant, and oxygen is the reactant that's present in excess. Finally, it's important to remember that just because we have more molecules of nitric oxide does not mean that it is the excess reactant. In fact, in this case, it's the limiting reactant because it reacts 2-to-1 with oxygen. We can see this more clearly if we reorganize the table to show the number of equivalent moles or equivalents. So even though we start with 8 molecules of NO and 7 molecules of O2, since nitric oxide reacts with oxygen in a 2-to-1 ratio, we take 8 and divide it by the stoichiometric coefficient, 2, which gives us 8 divided by 2 equals 4. And for oxygen, the other reactant, we take 7 and divide it by the stoichiometric coefficient of 1, which gives us 7 divided by 1, or 7 equivalents. Okay? And so we see that even though we have 8 molecules of NO and 7 molecules of O2, what we really have is 4 equivalents of NO and 7 equivalents of O2, which here clearly shows us that NO is the limiting reactant, since we have the smallest number of equivalents. A side reaction from the manufacture of rayon from wood pulp is given by the reaction shown here. In this example, we are asked to calculate the mass of Na2CS3 that is produced when 92.5 milliliters of liquid carbon disulfide reacts with 2.78 moles of sodium hydroxide. So the strategy for this question is to use the volume of carbon disulfide and convert this to moles of carbon disulfide, then to compare the moles of CS2 with that of NaOH to determine the limiting reactant. This will then give us the amount of product produced in moles, and then finally we would convert the moles to mass using the molar mass. So the best way to determining the limiting reactant is to compare the number of equivalents or equivalent moles for each reactant. Starting with the volume of carbon disulfide, which is 92.5 mils, we would then use the density to convert this to mass of carbon disulfide, and we were given the density as 1.26 grams per mil. You can see here that multiplying by the density allows us to cancel the volume in mils, leaving us with mass of carbon disulfide in grams. Next, we can convert mass to moles using the molar mass. So dividing by the molar mass, we can see that we can cancel the grams of carbon disulfide, leaving us with the moles of carbon disulfide. Multiplying this out in our calculator gives us 1.53 moles of carbon disulfide. Now, in order to convert this to equivalents, we would divide the moles of carbon disulfide by the stoichiometric coefficient, which in this case is 3. So here we have 1.53 divided by 3, which gives us 0.50 equivalents of carbon disulfide. Next, we convert the number of moles of sodium hydroxide, which was given as 2.78, and also divide this by the stoichiometric coefficient, which in this case is 6, which gives us 0.463 equivalents of sodium hydroxide. And here we can see that because sodium hydroxide has the fewest equivalents, sodium hydroxide is therefore the limiting reactant. Knowing the limiting reactant, we can now determine the amount of product produced. Starting with the limiting reactant, which was 2.78 moles of sodium hydroxide, we multiply by the stoichiometric coefficients, which is 2 for Na2CS3, and divide by 6 moles of NaOH. And we can see here now that the moles of sodium hydroxide cancel, leaving us with moles of Na2CS3. Finally, we can convert to mass of Na2CS3 by multiplying by the molar mass, which in this case is 154.17 grams per mole, which allows the moles of Na2CS3 to cancel, leaving us with mass of Na2CS3 in grams, which is the units that we want. Multiplying this out in our calculator gives us 142.8 grams of Na2CS3. Finally, we can see that because here we have 3 significant figures as the smallest number of significant figures in our data, we would round to 3 significant figures, which rounds to 143 grams of Na2CS3.